Finance. Today we are going to be talking about intelligent storage systems. So we would be giving you a brief overview that how exactly an intelligent storage system works and what are the key components of it. So let's start and go ahead with the session. So what is an intelligent storage system? Now, business critical applications require high level of performance, availability, security, and scalability. With advancements in technology, a new breed of storage solutions, known as intelligent storage system, has evolved. These intelligent storage systems are feature-rich RAID array that provide highly optimized I/O processing capabilities. These storage systems are configured with a large amount of memory called cache and multiple I/O paths and use sophisticated algorithms to meet the requirement of performance-sensitive applications. These arrays have an operating system that intelligently and optimally handles the management, allocation, and utilization of storage resources. It also supports for flash drives and other modern technologies such as virtual storage provisioning and automated storage tiering, which has added a new dimension to the storage system performance, scalability, and availability. Now, what are the key components of an intelligent storage system? An intelligent storage system consists of four key components: front end, cache, back end, and physical disks. An I/O request received from the host at the front end port is processed through cache and backend to enable storage and retrieval of data from the physical disk. A read request can be serviced directly from cache if the requested data is found in cache. In intelligent modern storage systems, front-end cache and backends are typically integrated on a single board, referred as storage processor or storage controller. Now let's talk about each component individually. If we talk about front end, the front end provides the interface between the storage system and the host. It consists of two components, the front end port and the front end controllers. Typically, a front end has redundant controllers for high availability. For each controller contains multiple ports that enable large number of hosts to connect to the intelligent storage system. Each front-end controller has processing logic that executes the appropriate transport protocol such as Fiber Channel, iSCSI, FICON, or FCOA storage connections. Front-end controllers route data to and from cache via the internal data bus. When the cache receives the data, the controller sends an acknowledgement message back to the host. Now let's talk about cache. I'm sure most of you must have heard about cache in your using your Internet Explorer or your Google Chrome. That it's temporarily saves the file so that whenever you're launching the same website next time, rather than taking up from the internet, it takes from the cache itself. It works similar to that. So cache is a semiconductor memory where data is placed temporarily to reduce the time required to service the IO request from the host. Now, cache improves storage system performance by isolating host from the mechanical delays associated with rotating disk or hard disk drive. Rotating disks are slowest component of an intelligent storage system. Data access on rotating disks usually takes several milliseconds because of the seek time and rotational latency. Accessing data from cache is fast and typically takes less than a millisecond. On intelligent arrays, write data is first placed on cache and then returned to the disk. Now let's get into a bit more detail. Like if we talk about read operation with cache, so when a host issues a read request, the storage controllers read the tag RAM to determine whether the required data is available in the cache. If the requested data is found in the cache, it is called read cache hit or read hit, and data is sent directly to the host without any disk operation. This provides a fast response time to the host, about a millisecond, and if the data request is not found in the cache, it's called a cache miss, and the data must be read from the disk. The backend access the appropriate disk and retrieve the requested data. Data is then placed in the cache and finally sent to the host through the front end. Cache misses increases the I/O response time. Now, similarly, if we talk about write operation with cache, a write operation with cache is implemented in two ways. One is write through cache and write back cache. In write through cache, data is placed in the cache and immediately returned to the disk, and an acknowledgement is sent to the host. Because data is committed to the disk as it arrives, the risk for data loss are low, but the write response time is longer because of the disk operations. Now, if we talk about write back cache, data is placed in the cache and acknowledgement is sent to the host immediately. Later, data from several writes are committed or destaged to the disk. Write response times are much more faster because the write operation are isolated from the mechanical delays of the disk. However, uncommitted data is at the risk of loss if cache failures occur. Now, cache can be bypassed under certain conditions such as large size write IOs. In this implementation, if the size of an IO request exceeds the predefined size, called write-aside size, writes are sent to the disk directly to reduce the impact of large write consuming a large cache space. This is particularly useful in an environment where cache resources are constrained and cache is required for small, random IOs. Cache is a finite and expensive resource that needs proper management. Now we manage cache through various algorithms, and the most commonly used algorithms are least recently used algorithm and most recently used. In least recently used, that it's an algorithm that continuously monitors data access in cache and identifies the cache pages that have not been accessed for a long time. LRU either frees up these pages or mark them for reuse. This algorithm is based on assumptions that data that have not been accessed for a while will not be requested by the host. However, if page contains write data that has not been committed to the disk, the data is first returned to the disk and before the page is reused. And in most recently used, the algorithm is opposite of LRU, where the pages that have been accessed most recently are freed up or marked for reuse. This algorithm is based on assumption that recently accessed data may not be required for a while. Watermarking is also an important part of cache management. As cache fills, the storage system makes the action to flush dirty pages to manage space availability. Flushing is the process that commits data from cache to the disk. On the basis of I/O access rate and pattern, high and low level called watermarks are set in the cache to manage the flushing process. High watermark is the cache utilization level at which storage system starts high speed flushing of cache data. Low watermark is at the point which the storage system stops flushing data to the disk. The cache utilization level increase the mode of flushing to be used. Now idle flushing occurs continuously at the modest rate when cache utilization level is between high and low watermark. High watermark flushing activated when cache utilization hits the high watermark. The storage system dedicates some additional resource for flushing. This type of flushing has some impact on I/O processing. Force flushing occurs in an event when a large I/O burst when cache reaches 100% of its capacity, which significantly affects the I/O response time. In force flushing, system flushes the cache on priority by allocating more resources. It's similar to, we can say, the water tank, where we set certain limits that till this limit the water should be idle flushing, and the HVM we can set on our own that depending upon the needs that which level we should mark it, a higher watermark or idle flushing. Cache is a volatile memory, so a power failure or any kind of cache failure will cause the loss of data that is not yet committed to the disk. The risk of losing uncommitted data held in cache can be mitigated using cache mirroring or cache vaulting. Cache mirroring is a technique where each write to cache is held in two different memory locations on two different independent memory cards. If cache failure occurs, the write card will still be safe. Write data will still be safe in the mirrored location and can be committed to the disk. It is similar to your RAID 1 array where your data has been mirrored, and here your write only your since your only your write data is cached or write data is mirrored, we can have retrieve the data in case of any kind of failure of the disk or if the any kind of disk or independent memory failure. The other technique is called cache vaulting. Cache vaulting helps us in whenever the possibility of data loss due to any kind of power failure. So what it does is it keeps on powering the memory with the battery until the AC power is restored or using a battery power to write the cache content to the disk. If an extended failure occurs, using batteries is not a viable option. This is because in intelligent storage system, large amount of data might need to be committed to numerous disks, and batteries might not provide the power sufficient time to write each piece of data to its intended disk. Therefore, storage vendors use a set of physical disks to dump the content of cache during the power failure. This is called cache vaulting, and the disk used for this purpose are called vault drives. When a power is restored, data from these disks is written to the right cache and then written to the intended disk. We can also improve the performance dramatically by using the intelligent caching software and PCI flashcard on the host. This improves the application performance by reducing latency and accelerate throughput. Server flash caching technology works in both physical and virtual environments and provide performance acceleration for read-intensive workloads. This technology uses minimal CPU and memory resources from the server by offloading flash management into a PCIe card. Getting back to our key components of ISS, the backend provides an interface between the cache and the physical disk. It consists of two key components, backend ports and backend controller. The backend controls the data transfer between cache and the physical disk. From cache, data is sent to the backend and routed to destination disk. Physical disks are connected to the port at the backend. The backend controller communicates with the disk when performing reads and writes and also provides additional but limited temporary data storage. The algorithm is implemented on the backend controllers provide error detection and correction along with the read functionality. Now the last key component of ISS is physical disk. Physical disks are connected to the backend storage controller and provide persistent data storage. Modern intelligent storage systems provide support to a variety of disk drives with different speeds and types such as FC, SATA, SAS, and flash drives. They also support the use of mixed flash, FC, or SATA within the same array. Now, to conclude, intelligent storage systems can help dramatically improve the performance of a particular storage array. Now, in today's world, where most of the companies are moving their data to a cloud based environment, this kind of solutions can definitely improve the latency that is caused by the network bandwidth issues to access any particular data. If you want, I hope I was able to give you a brief overview that how exactly intelligent storage system works. To get regular updates or regular webinars, you can please follow us on facebook.com at facebook.com/academic alliance. Thank you. Have a good day.